So the normal distribution, if something is normally distributed, then it has a bell-shaped distribution. Do you remember when we looked at the histograms and you had some of the histograms that they go up and then they go back down, the bars do? Those were normally distributed, or they were normal, meaning they kind of have that bell shape to them, like this graph here. Have this bell shape to them. And you also hopefully remember when we went over z-scores. I know that we didn't spend a lot of time on that. We're going to be using z-scores in the next few sections, really throughout the rest of the book, to do a lot of cool things. Remember, your z-score was equal to x minus mu over sigma. Okay, and all these numbers down here on the bottom, these integers on the bottom of this bell curve, those are all z-scores. Remember when we went over empirical rule that said if you're within 1 standard deviation of the mean, then that contains about 68% of all of the data? May or may not remember that. If you're within 2 standard deviations of the mean, it contains about 97% of the data, I think it was. And then if you're within 3 standard deviations of the mean, it was like 99 point something % of all the data. And so we use that normal distribution to help figure out a lot of things like probabilities. Once we normalize a number, once we use the z-score and we put it in a form where we can use this bell-shaped curve to figure out stuff about the data values, then you'll see that it makes a lot more sense than some of the stuff we've been going over. I promise you. Remember that the probability for something occurring is 1. So if you add up all the probabilities for something occurring, if you add up all the events, you get 1. The area under this curve, the total area, both this shaded region and this on both sides, if you add all that together, it's equal to 1. Okay, so that comparison is very important that you understand. We're using these areas under the curve to find probabilities if they're normally distributed. What's a normal distribution? You have small, and then it goes up, and then it goes back down. Since all normal distributions are symmetric, the mean, mode, and median are all equal. Okay. The total area under any normal curve is always equal to exactly 1. So that's a pretty easy concept to understand. That total area is equal to exactly 1. Now, if you knew calculus, the density function would be super important. And so if you want to know how people got these values out of the tables, they used the density function. Now the density function is probably a little bit more math than you would want to do. You may say, well, hey, we've done some pretty complex formulas in here. Well, the density function is, like I said, a little bit more complex than what we've been doing. Let me show you what it looks like, the density function for a normal distribution. When I show you this, you'll probably just say no thank you. because it is a lot more complex. And of course, this could all be written in different ways to make it look a little simpler. But you can actually use this function with a little bit of calculus to figure out the area under the curve so that you don't need the tables. Okay? Which is kind of neat. That's the way if you were taking a math-based, usually it's junior, senior level statistics class, then you would use the calculus to figure out those probabilities, or you could. Your book does point out this formula doesn't look very normal, but that is the density function for a normal distribution. All right, I'd said something about histograms. Remember, at one time we were looking over histograms. Some histograms you can see the pattern, starting out low and then going high. It's approximately on this one. You see that goes down and then back up. This is straight out of your ebook. This one is a little bit, you can see a little bit easier. This one here, you can see as n gets larger, the normal distribution is more apparent. It's almost like if we were able to trace the outside of each one of these rectangles, then it would form that bell-shaped curve. Okay, and so that's the end of